Okay, it looks like we're recording. This is for Astronomy 320, Sacramento City College. It's July 27th, 2020. Okay, I just want to show you. So the online number 9, the one we're doing right now, it's up on the it's this one right here. So it's up here. Okay, it's up already. And also, okay, quiz number 6. You may get this before tomorrow morning because I don't know if this is going to be very long. So that one goes with online lecture number 8. The one for 9, and the next one I'll do tomorrow will be for the final exam. Okay, and then the PowerPoint that we're going to look at is this one right here. So it's up there already too. Okay, so let's go over to the PowerPoint, and here it is. I didn't go to the beginning of it, but okay, it's section 17.1. All we're going to do between now and tomorrow is cover 17.1, 17.2 tonight. Then I'll do one more video and PowerPoint and or online worksheet for section 18.4 about the Hertzsprung-Russell diagram, HR diagram. Okay, this one starts off talking about luminosity. Luminosity is a measure of the brightness of a star. It's the total amount of energy of all wavelengths a star emits per second. Okay, if you know anything about wattage, that's joules per second, and so power is joules per second. So it's basically kind of like the power output of the star. Okay, so basically we can answer this one right here. Oops. So what is luminosity? It's the total amount of energy the star puts out per second. It's how bright the star is. Okay. So astronomers express luminosity of other stars in terms of the sun's luminosity. So we say the sun maybe has a luminosity of 1. Okay. Then Sirius, the dog star, is 25 more times more luminous than the sun. So we'd write L sun luminosity of Sirius is equal to 25 times the luminosity of the sun, just as an example. Okay, apparent brightness. Okay, brightness of stars. Apparent brightness is how bright a star appears from Earth. Okay, that is not a level playing field because a very, very bright star very far away may look very, very dim. And a not so bright star that's very, very close could look much, much brighter. That's the thing with Sirius, for example. Compared to a bunch of other stars like Betelgeuse and Rigel, Sirius is not as bright as they are, but it's closer to us than they are, so it appears brighter in the sky. Okay, it's the brightest star in the sky, right here. This one right here, Sirius. So here's an example I got from someplace. Distance from Earth. Here's this big bright star that's further from the Earth. Here's this not so bright star. So this could be like Rigel. This could be like Sirius. And it's not so bright star, but look, they can look the same brightness from Earth. Maybe even B, the closer one, looks a little brighter like it does in the case of Sirius. So basically, apparent brightness is not a level playing field. We also have absolute brightness, which unfortunately we're not going to be able to get to. I think we talked about it earlier in the semester. Stars emit their radiation equally in all directions, so only a very small amount reaches the Earth. So when you look at a star at night, that's only the light that made it to your eyeball. You can imagine all these different directions that same amount of light would go to in a circle or a sphere, actually, a sphere around that star. Anywhere you go in that sphere around that star, equal distance from the star, anywhere in the galaxy, you'd see the same thing basically. Okay, so that same amount of energy that's going to your eye that causes your rods and cones to fire and send signals up to your brain, that's the same amount of brightness that's going everywhere else within that same distance. And if we get closer, we get more energy. If we get further away, then the star is going to look dimmer and dimmer. An extremely luminous star very far away will appear very dim on the Earth. Okay, there's stars that are just enormous, very incredibly bright, but because they're so far from the Earth, we can barely see them. A star of medium luminosity but close to the Earth will appear much brighter. So apparent brightness, which is the second question we have over here, that's how bright the star appears on the surface of the Earth. and it is not a level playing field. A level playing field, I think we talked about earlier, absolute brightness, we imagine they're all exactly 10 parsecs away. And now we got the scale, and don't know why astronomers do it like this, but here's the scale we got. The scale, it's weird because the big high positive numbers are the dimmest, and the big negative numbers are the brightest. The sun, without a doubt, is the brightest thing we see in the sky. Okay, it's a very, very average star. Okay, it's very, very average, yet it's so close to us, it looks incredibly bright. It dominates. It basically dominates. Okay, it would be minus 26.8. A full moon is minus 12.5. Okay, you got Venus at its brightest, minus 4.4, Sirius minus 1.5, Alpha Centauri, Betelgeuse is much brighter than Sirius at 10 parsecs away, but it's further away than Sirius, so it appears dimmer from the Earth. Polaris, the North Star. Naked Eye Limit. Naked Eye Limit is right in there, what is it, about 5. Then Barnard Star is at 9.5. So here's the closest star to the sun, yet it's a little tiny red dwarf. And as a result, we can't even see it. Naked eye. We have to use binoculars, barely we can see it. With binoculars, 1 meter telescope, then we can see it much better. Okay, so Barnard Star, and so we can answer the next two questions here. Okay, so what is the apparent brightness of the sun? Now it's minus 26.8. The average person with average eyesight, standing in Sacramento, could they see Barnard Star? I'd say absolutely not. Matter of fact, I think this table here is for people with very, very good eyesight, being someplace out in the desert away from light pollution. So they wouldn't even be able to see Barnard Star, because look, naked eye is 6. If it's like 6, 5, 4, or into the negative numbers, we can see it. If it's 6.5, we can't see it. 9.5, we can't see with the naked eye. So the answer would be no. So already up to the colors of stars. Stars come in many different colors. Very hot stars radiate more in the higher energy blue part of the spectrum. Remember, I mean, it's been within like the last 4 weeks, but it seems like an eternity ago now. But we talked about the electromagnetic spectrum, and you had the visible part of the electromagnetic spectrum, the Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And remember that we said that the red towards the radio, that has the lowest energy. The blue, indigo, violet, they would have the highest energy. So red stars would be cooler, lower energy. Blue stars would be hotter, higher energy. Okay, stars with the coolest surface temperatures radiate in the lower energy red part of the spectrum. The sun fall. Okay, nice. Then very hot stars radiate more in the higher energy blue part of the spectrum, and stars with the coolest surface temperatures radiate in the lower energy red part of the spectrum. The sun falls in the middle, and yellow dominates for the sun. Sun would be someplace in the middle. Hopefully we'll see that when I get up the stuff about the HR diagram. And then here we just have a table. I think that's it. Okay, on the table. Now this is surface temperature. So blue stars could have an average surface temperature about 25,000 Kelvin. Now we talked about what Kelvin was. Okay, absolute Kelvin is 0 Kelvin is absolute 0. Okay, so Spica, so that it's somewhere close to 25,000 degrees Celsius, as a matter of fact. You would only have to add 273 to whatever you have. You would subtract, whatever you have in Kelvin, you'd add 2, so it'd be 25,273 degrees Celsius here. Spica is an example. Now if they appear white, like Vega, okay, that's about 10,000 Kelvin. If they appear yellow, the surface temperature is about 6,000 Kelvin. That's our sun. Now we get to the cooler stars. So they appear orange, you're down to 4,000 Kelvin. That's Aldebaran. And then the red ones, the coolest surface temperatures, the lowest energy, that's going to be Betelgeuse. You may say, well, why is Betelgeuse so bright if it's so cool? Well, because Betelgeuse is enormous. It's got a huge surface, huge surface. So even though it's not radiating as much energy per surface area, per unit surface area, there's so much surface area that it's going to end up radiating a heck of a lot of energy. Okay, and that is it. So we can go back and take a look over here. And what color would be the hottest stars? Would be the hottest stars would be blue, and the coolest stars would be red. Our sun would be yellow. It's somewhere in the middle there. How does the surface temperature of a star compare to where the color appears on the electromagnetic spectrum in terms of energy? Well, remember, if we just look at the visible section, we remember that Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Okay, well, red is the lowest of those energies. That corresponds to the coolest stars. Then the brightest stars appear blue. Okay, so they would be the hottest. They would be of the stars, and so they would be the hottest surfaces, more energy. Okay, that's everything. Okay, just once again, here's the plans. So the exam on Thursday, the exam will cover everything after the first exam. So where we stopped at the first exam, everything after that, and the only new stuff you have to worry about between now and Thursday is Chapter 17, Sections 1 and 2, and Chapter 18, Section 4, which hopefully I'll have all that stuff up tomorrow. Okay, so that'll take care of the semester, and I'll have one more video, and I'll look into having a Zoom conference on Wednesday. I gotta see. I'll do that tomorrow. I'll look into it tomorrow, and I'll send out a thing if I'm going to be able to figure out how to have a Zoom conference on Wednesday. All right, so I think that's everything. This is pretty short, so it shouldn't take more than maybe a couple hours for me to upload this. It's 8:49 right now, so maybe I'll be sending you something around 10:49 or 11 saying that the video is up. Okay, talk to you later. Good night.